rational. Okay? And the binary operation is just multiplying two matrices together. Okay? Is that a group or not a group? It's more subtle. Now my suspicion is this, right? The fact that B has to be Q, a rational. So I'll play devil's advocate and I'll say, well, what if, see, A and C can be R reals, right? So I can have an irrational, like for example root 2 or something, amongst the reals. So if I multiply something here, so if I put like square root of 2 here and root 2 here or something, and then I multiply them out, I won't actually do it, but I'll end up with something with the square root of 2 here, right? So that means my result. If you actually do it, so you put root 2 and whatever, and I'll end up getting once I do the matrix multiplication, I'll end up with a root 2 in this position where B is. But B has to be a rational. But if I've got a root 2 here, that's an irrational. So not closed. Right? It's not closed for any two elements of your set. There's an infinite set, right? You've got huge number of possibilities. So I only have to find one counterexample. So if I put like root 2 here, I'll end up with a root 2 something here, and that's not rational, so it doesn't fit that form, so it's not closed, right? Because the result doesn't belong to this set, because that's a rational, this is an irrational, so not a group. Okay. All right, now I won't actually do it, but I'll state the problem for you and ask you to do this as homework. You're given a set of 4 matrices. So here's your set. You've got 4 matrices, and you're asked to show that this is a group. So 1, 0, 0, 1. We're just looking at that. That's going to be your unit matrix, right? It's well known. Okay, -1, 0, 0, 1. And 1, 0, 0, -1. And -1, 0, 0, -1. So you could call, let's call that I, because it's obviously the unit matrix. We call that B, sorry, A and B and C. Show that it's a group, right? So how to do that? Well, I suggest you could do a table. Now it's going to be tedious, right? So if you make a table, you're going to have I, A, B, C. This is your group table, I, A, B, C. And you're going to have 16 entries. Right? So a bit of work, because you've got to multiply all these matrices. I won't do it, it's too tedious, take too long. But this is a suggested approach. So create your group table and have a look at the results, and if all the answers belong, each of the 16 answers belongs to one of these, so it's closed, okay? That's the unit matrix. Proving associativity, woo, tough, that's hard. Okay, that'll be the tough part. Proving that it's associative, because well, let's how many cases have you got? So you have to prove this. So how many cases? You've got 4, 4, 4. You've got 64 cases. Ooh, that is tedious. Definitely not doing it. Okay, so to prove associativity, you have to show that this is true for all cases, right? So you have four possibilities here, four here, four here. And so 4 by 4 by 4, 64 cases. Tedious. All right. So assume it works after a lot of work. So associativity is done. Got the unit. Now how about the inverse? Well, for each of these matrices, which I've relabeled by letters, like I, A, B, C, by looking at the table when you do it, you'll be able to see what the inverse is for each one. So A by one of these will give you I. So you can find the inverses for each element. So the inverses exist. So you show then that this set of these 4 2 by 2 matrices is a group, right? Because it satisfies the 4 criteria. But the proof of associativity, painful. 64 cases. Maybe there's a smarter way if you can think of it. All right. Now the last question with 7 parts, fairly quick. True or false type questions. Okay. 1. Every element of a group has an inverse. Is that true or false? Well, the very definition of a group is that every element must have an inverse, right? So it's true by definition. So 1 is true, right? 2. It's possible for an element of a group to be its own inverse. So they're saying it's possible for an element, one, just not all elements, just one element, to be its own inverse. Well, the obvious example would be the unit. So E is just E, right? So that's true, right? So it is possible for an element, one or more, of a group to be its own inverse. And here's an example, the unit. Okay. It is not possible for a group to be infinite. Nonsense. That's nonsense. I mean, the set of all integers and the binary operation plus, that's a group, right? But it's infinite in size because there are an infinite number of integers, right? So it is not possible for a group to be infinite. That's false. Here's a counterexample where it is infinite. Okay. It is not possible for a group to consist of a single element. That's not true either. You can have the simplest group is just the unit. Now it has to be. If you just have one element, it has to be the unit, right? Because otherwise it's not a group. A group has to have the unit matrix, the unit element. So the simplest group is just of order 1, just one element, one member, and it has to be E. Because if it's not E, it's not a group, because it does not have the unit. All right? Okay, part 5. No element of a group has order 1. Now we're talking now about the order of an element, not the order of a group. Right? No element of a group has order 1. That's not true. Let's find a counterexample. Of order 1. Well, or just E. Yeah, just E. Because E to the 1 is E. Right? So no element of a group has order 1. So E has order 1, right? Because E to the 1 is E. So that's false, right? If the order of an element X is n, little n, so if the order of an element, so here's your X, and that's your order, little n, and X to the n is E, then n, big N, divs little n. it's the other way around, right? We did the theorem. So if that's true, that's E, right? So if that little n is the order of the group, sorry, the order of the element. Yeah, it's easy to get those two confused. Okay, so if little n is the order of the element, by definition, you've got that. Okay, and you're given this, then we did a theorem just a while back that little n divides big N, but here they're saying the reverse. So that's wrong, right? It's the other way. Little n divides big N, not the other way. All right, that's it. A very long lecture because the chapter was twice the length of the others, as I've said several times already. Now, the next lecture, lecture 6, instead of talking about groups, we will talk about subgroups. And what's a subgroup? Well, it's a subset that is also a group. Right? So it uses the same binary operator as the group. And because this subset is also a group, it means it also has a unit and all the 4 criteria. And subsets are interesting because you can start asking questions like, well, if you know the order of the group, and say it has a subset, which is a group, so it's a subgroup, so you can know the size of the subgroup, right? So you know the subgroup's order. Is there some kind of relationship? You can start asking questions like this. You can start asking, well, is there some kind of arithmetic relationship between the size of the group, so the group's order, and the size of the smaller group, the subgroup, its order? So is there some connection? And I'm giving you a taste of what's to come. In fact, this question I've just posed, its answer is a very famous theorem connected with subgroups, but that's the next lecture. So, I'm tired. When I get tired, I make mistakes, as you saw. So I'll stop there until next time. Ciao.